All right. Okay, great. Thanks again, Victor. So I think we are about to, kick up the second day. So again, we will begin with a very exciting keynote. It's my great pleasure to introduce today's keynote speaker, Jaideep Dastidar, who is currently a senior fellow at AMD. So Jaideep actually, has multiple important roles at AMD. He's the SoC architect of the Domain Specific Accelerator, and also, this the Adaptive SoC, right? And he's also the lead architect of this AMD 400G Adaptive SmartNIC and DPU SoC. So this is something that he's going to talk about today. Before AMD, he was a distinguished engineer at Xilinx. He also worked at Freescale and HP Enterprise. Okay, so without further ado, please join me in welcoming Jaideep.
Thanks, Joe. Hey, good morning, everyone. So today I'm going to talk about the FPGAs and their evolving role in domain-specific architectures. For the agenda, what I will do is I'll start by a brief historical survey of FPGAs and how they've evolved in terms of their applications, in terms of domain-specific accelerators. I'll then move on to doing a compare and contrast between adaptive SoCs and domain-specific adaptive SoCs. And in giving you that comparison point and the pros and cons of each, you'll start to see which application spaces would benefit from such an approach, which application spaces would still want to stay within the traditional adaptive SoC architecture. And then I will put the spotlight on AMD's 400 gig adaptive SmartNIC/DPU SoC. But by that point in time, you will already understand some of the trade-offs, so then we can get deeper into the specifics of that SoC. And by that point in time, hopefully you're beginning to see, okay, these are the trends, these are the considerations, and give you an insight into future potential domains for which we will build adaptive SoCs. So historically, of course, Xilinx's humble beginnings started as FPGAs as a sea of gates. And then over time, we added other IP, the fundamental LUT structures were enhanced with DSP structures. We added analog IO, high-speed IO, we added high-speed transceivers. And then as we went from the progression of 28 nanometer to 16 nanometer, we started adding system-on-chip components. Hardened controllers, a processing subsystem, so the Zynq UltraScale MPSoC family started adding some system-on-chip components to complement the FPGA and to assist with, loading bit streams and authenticating them and such. And then finally, the Versal 7 nanometer platform introduced even more technologies to complement at a system-on-chip level the fundamental innovations in the FPGA. A big part of it was the NoC, the network on chip. So now you no longer have to use dedicated fabric resources to have PL to PL data movement or these other hardened IPs in terms of the family of IPs we were adding for data movement across those. And of course, we also had a significant uptick in the other hard IP components, most notably the AI engine, which was announced with the part of the first Versal family of products. Now, before I move on to changing the spotlight to domain-specific SoCs, I just kind of wanted to point out that, we didn't abandon the past and just look towards the future, right? If you think about it, even today, AMD Xilinx continues to have a keen focus on the fundamental concepts of the sea of gates. So the VU19P, having 9 million logic elements, is a key SoC for the emulation, test and measurement markets. So all the innovations that we were adding on to other product lines or product types, we also backfilled into the sea of gates concept. And that trend you will see continuing just as we propagate forward technologies from previous generations that have seen widespread adoption, you're going to see that kind of consolidation actually now across markets. And the domain-specific adaptive SoC I'm going to talk about today is that kind of collection of previous ideas that resonated with our customers. And we enhanced those things, and then we added new technologies and new innovations to the SoC. So both the Zynq UltraScale Plus family and the Versal family have led us to create a new type of product, which is the domain-specific adaptive SoC. And some examples of which are, of course, the RF SoC from the 16 nanometer technology. So we focused on the RF domain and added significant hard IP, both analog and digital, to assist with the RF domain due to the challenges in terms of modern day wireless standards and networks of massive MIMO and such. And then the focus of today's talk is similarly, we took the foundational technologies from Zynq UltraScale Plus and Versal, the first family of Versal devices, Versal Premium, Versal Prime. And we use that as a starting point to overlay a SmartNIC/DPU domain adaptive SoC. Now, while the focus of this talk today is, of course, on the technologies that led to the 400 gig adaptive SmartNIC/DPU SoC, I just kind of wanted to point out that, as recently as a month ago, our CEO announced two very diverse product lines. One is Ryzen AI and the other is the V70. And they both leverage the foundational technology of the AI engine that was first launched with Versal. So that's maybe another talk for another day, but just wanted to point out that as I'm showing you a proliferation of new product types and families, this fundamental technology that we built in previous generations is also propagating into new form factors and devices. And actually a shout out to the university program. They have the Alveo V70 card, and they also have the RF SoC. So if you wanted to go check them out, you can take a look there. So what are the general motivating factors behind domain-specific adaptive SoCs? To make the case here, I'm going to focus on compute acceleration, where FPGAs have played an increasing role. So on the x-axis is the application space, on the y-axis is performance per watt, and in some cases you can also use the y-axis for raw performance. So starting with the gray parabolic curve, there's the known general purpose CPUs, right? They've gone through a rapid advancement in terms of their capabilities, and they continue to offer a very, very diverse set of application space because of the software programmability of it. Now, where traditional adaptive SoCs and FPGA-based accelerators come in is you kind of have to get a steeper slope on the performance and performance per watt angle, and you trade off that with a narrower application space. So the area under the curve of the gray line is, of course, significantly higher than the area under the curve of the traditional adaptive SoCs and FPGA-based accelerators. However, there are certain domains where you do want uncompromising performance per watt or uncompromising raw performance. And so for that, we've created a new architecture for domain-specific adaptive SoCs. And as you can see, the parabolic curve of the blue lines is very steep, but the trade-off is it's a narrower set of domain-specific applications that you can apply those types of SoCs to. Now, specific to the SmartNIC and DPU market, there are other motivating factors behind which a domain-specific adaptive SoC will play really well. There are several trends in the industry in terms of both hyperscalers and enterprise cloud customers, where these trends are actually leading towards a collision course and somewhat of an impasse. One of the trends is the explosion in virtualization. It's very attractive for a lot of software engineers, especially in disaggregated applications, to offer customers multiple instances out of one server, so that they can have large instances, small instances, and then they virtualize that so that they can have live migration, they can have their disaggregated storage anywhere. And level of virtualization has also gone through another kind of explosion, which is due to containerization. So instead of just guest OSs and multiple instances of guest OSs, you have many orders of magnitude higher number of lightweight containers that enter and exit very rapidly. Another trend, I think Andy Bechtolsheim has spoken about this multiple times, is kind of an explosion in the network port bandwidths, far outpaced Moore's law. So, in the span of a few short years, you went from where the industry had 10 gig Ethernet, and then it rapidly moved to 25 gig, 40 gig, 100 gig. And really the processing demands of moving network packets, and then on top of that, other overlays on top of those TCP/IP packets, RDMA, RoCE, and such. When you combine that with the number of virtual machines that you're trying to provide those services to, you've got another trend that's kind of headed towards a collision course. And then lastly is the software-defined networking movement, which has now proliferated into software-defined storage and such. So why was software-defined networking so attractive? It allowed the end customer to create, software engineers could create the rule set and such for networking. And more importantly, they were hardware agnostic, right? So they could create virtual switches, virtual switching functions across multiple VMs and such. And they didn't have to be tied into a specific hardware solution to achieve that functionality. And then lastly is the rapidly evolving set of use cases. And I think, it would have been a hypothetical conversation 2-3 years back, but you can imagine, just 2-3 years ago, everybody was worried about social media, about news feeds and fake news and such. And that was all text and maybe a few pictures. And now, the social media movement's all about, short clip video. Similarly, enterprise and corporate communication tools and collaboration tools, thanks to the COVID, you've had a drastic increase in people video conferencing from home, VPNing, multiple connections. So you have a situation here where the industry, the infrastructure for enterprise cloud and hyperscalers, they have to adapt very quickly, right? They can't suddenly go there and overhaul their existing networks and networking capabilities. So that's now kind of table stakes, right? It's a lesson learned, and they're going to have to be very adaptive to changing circumstances. So the combination of all these trends has led to an ever-increasing burden on the host CPU in the data center. And the combination of virtualization, high network bandwidths, therefore you're going to be doing packet processing at very high rates, the fact that there's a large software stack doing software-defined networking, and the fact that you have to quickly change to new use cases or optimizations for your existing use cases. There was a paper published by one of the hyperscalers a few years back, and in their study, they had estimated that up to 30% of the CPU was spent not running the multi-tenant applications, but just running data center infrastructure overhead. So in our case, the performance needs, the diversity of use cases, the rapid evolution of those use cases, and the level of virtualization led to this particular domain being very attractive in architecting a domain-specific adaptive SoC. And the main purpose is, just as FPGA-based and adaptive SoC-based off-roll acceleration would offload that CPU from performing functions that could be done way better at higher performance per watt. The V70 is an example of inference. This particular adaptive SoC would then offload all these functions, virtualization functions, disaggregated storage, multi-tenant networking into the adaptive SoC. So in architecting the solution, just kind of wanted to take some big picture themes, and then I'll play them out into the comparisons between adaptive SoCs and domain-specific adaptive SoCs. So since this is an FPGA conference, on the figure on the right, we'll start at the 4 o'clock mark. So at the 3, 4, and 5 o'clock mark, I as I mentioned earlier, the data center networking domain and the SmartNIC DPU domain, you have to deal with rapidly evolving use cases. At the same time, you need the velocity at which you can deploy new infrastructure fast and at scale. So, FPGAs are particularly well suited, right? You can add or remove new functions. You can optimize functions and swap them out through partial reconfiguration, dynamic function exchange. Different points in the data center could have different use cases optimized in the FPGA overlay. And then specific to networking, a lot of hyperscalers have optimized. They don't need to follow the industry standard, especially between software-defined networking and other packet encapsulation standards. They can have custom header extensions. They can optimize their data center network one step further. And they have the domain expertise in-house to make those optimizations and deploy it at scale. And so that's another place where an FPGA-based adaptive, domain-specific SoC has a particular advantage, because you don't need to come up with the kitchen sink of customizations across hyperscalers. You offer the programmable logic element, and then you architect the rest of the subsystem so that you can take advantage of custom headers and custom encapsulations of Ethernet standard packets. And then similarly at the 5 o'clock mark, you can, if you want, go back to the traditional FPGA-based adaptive SoC paradigm, where you're doing full custom data plane offload, because you have a specific pipeline that you want to, for security purposes or firewall or deep packet inspection purposes. You can do a full custom data plane offload in the FPGA fabric. Now, as we go from the 4 o'clock mark counterclockwise to the 12 o'clock mark, as the FPGA has to interact with the fixed function logic or the ASIC logic, we've created domain-specific hardware or hard IP offloads, right? So a classic example is crypto offload. There are a lot of NIST standards that are used everywhere in terms of the data center for storage and networking applications. So you can apply hard IP to crypto offload. And now in, for example, a Verso premium line, we did have hard IP accelerators. But as I go through this talk, you'll see we've deployed this particular crypto offload hard IP in a specific way to achieve that higher performance and performance per watt. Similarly, DMA offload, data movement, whether there's data movement on the PCIe host side or data movement on the network side, you can offload that functionality into a purpose-built fixed logic subsystem. And then you can also do network data plane offload, because like, as I mentioned, even if you're doing custom encapsulations, perhaps up to the first order, you still have an IPv4, IPv6, or IPsec packet, and you want to parse, classify, and figure out the rule set for that particular flow. And so that's also done, can be done in fixed function logic for the invariant portions of the Ethernet standard and Ethernet networking. Similarly, if we start at the 4 o'clock point and move clockwise, we have similar, interactions between the processing subsystem and the programmable logic, and I'll speak to that in more detail. But between the 4 o'clock mark and the 12 o'clock mark and the 4 o'clock mark and the 8 o'clock mark, you see two, ASIC to PL adapters and software to PL adapters. So on the ASIC to PL adapters, you can now put programmable circuits that interact with the hard IP. So you can either do programmable logic to programmable logic functions, all within the programmable logic, but then as you interface with the hard IP, you have to have some hardened protocol specific interfaces. And so you create programmable circuits accordingly. And similarly, on the processing subsystem side, you can create from a software perspective, you can create a traditional core, processor core to IO device interactions, where the IO device just happens to be a programmable logic device. So the core thinks it's an IO device and is doing MMIO reads and writes, and those MMIO reads and writes are actually going to PL memory. Similarly, the programmable logic agent is DMAing in, and it goes through IO coherency semantics with the processor, interrupts and such. So we offer, even though it's really a hardware, but it's really a software program that is running on a core that's interacting with the programmable logic device. And the programmable logic device, as far as the software framework is concerned, is essentially an I/O device, an I/O agent. So we created, adapter interfaces between the software domain, so to speak, and the programmable logic domain as well. And then certainly, since you have hardened subsystems like the processing domain and the fixed function ASIC domain, you can have domain specific interfaces between those two. And I'll give you some examples of domain specific interfaces between those two subsystems as well. So let's take a step back and then look at some general concepts behind how you would interact with a traditional adaptive SoC and how that would change with a domain specific adaptive SoC. And as I said, I want to give you an abstract picture so that even though later on I deep dive into the specifics of the networking domain, you can take these concepts and you can see how our line of thinking is towards other domains in the future. So one of the first things that will jump out at you in terms of a traditional adaptive SoC versus a domain-specific adaptive SoC is the amount of hardened logic, right? And that hardened logic can be a combination of domain-specific hard IP, domain-specific I/O. The processing subsystem is significantly larger. And the focus is less so on the programmable logic. And so because of that trade-off, since we're going after performance per watt and performance within a particular power envelope, we are reducing the amount of programmable logic and trading that off. A traditional adaptive SoC is still traditionally FPGA heavy, and I'll explain what the benefits are of the approach on the left-hand side, as well as the approach on the right-hand side. So we'll go through some details in terms of how you would interact with a traditional adaptive SoC. So one of the few attributes of a traditional adaptive SoC is, for example, the external I/O insertees. So the external I/O insertees is highly flexible. The gigabit, multi-gigabit Ethernet transceivers or the multi-gigabit interlocking transceivers and such are actually one piece of analog IP that is multi-mode, and that also has some additional digital functions for protocol-specific processing. So because of that, because it's multi-mode I/O, you now have some protocol-specific interfaces to the PL, and this gives you the full flexibility for you to put a domain-specific overlay in the programmable logic. So you could have one overlay, for example, that uses these multi-mode gigabit transceivers as for the Ethernet protocol. The other one is using the same SerDes, but for the interlocking protocol and interlocking data rates or fiber channel protocol. The other attribute of the traditional adaptive SoC is the platform IP. So even in the Zinc UltraScale days, you had the CMAC, and then in Versal, you have the DCMAC, the MRMAC, and technically the PCIe controller, PCIe-B controller is also a MAC, right, for the PCIe interface. So you have traditional hard IP, but that traditional hard IP is collared, it's surrounded by programmable logic. So now you can pick and choose which protocol, which hard IP accelerator you want to do attach to, and at where in your pipeline you want to attach those platform IP components. So once again, because of those IPs have specific protocols, for example, the high-speed crypto accelerator or the DCMAC or the MRMAC, the interface, the programmable logic interface to those are specific to that IP. And so you have a protocol-specific interface or accelerator-specific interface that you interact between the programmable logic domain and the hardened IP domain. And that's how you can see, in the white parabolic curve, the area under the curve was larger than that of a domain-specific adaptive SoC, because now the user logic has a lot more flexibility to stitch together and put in different modes and different protocols. So the same physical adaptive SoC could be used to deploy the high-speed crypto AES GCM encryption, in one case for the fiber channel protocol, and in another case for the Ethernet protocol. And so you as a user deploy the FPGA resources to stitch together those accelerators. So as you can see, through that, you need more programmable logic because you're doing more than just processing in the programmable logic. You're creating the pipeline. And you also, as a trade-off, get a very wide variety of applications that you can deploy. So for example, even within the networking space, if you took an adaptive SoC, we have customers taking this exact same SoC, and some customers are using it for data center interconnect. Others are using it for firewalls. Some of them are using it for security applications. And then if you wanted to take it one step further, maybe you can have redundant connections so that you can look for attacks through your network. So the exact same adaptive SoC is giving you a range of flexible overlays, and you craft your overlays the way you want it. Nothing is pre-configured for you, so there's a great deal of flexibility. On the flip side, now you are doing a lot more in programmable logic. So every time you go from the hard IP frequencies, which are already in the gigahertz range, and you go into the programmable logic, you have to drop down to the hundreds of megahertz range. And so there's that trade-off. You need more programmable logic, so you're consuming more power. And so now you can begin to see where traditional adaptive SoC is trading off a great deal of flexibility, even though it's offering a lot of hard IP components for power and maybe higher performance, but at a higher power envelope. So a good example is the Versal Premium device. So on the left hand and the right hand, you've got a whole host of gigabit gigabit transceivers. These transceivers, the GTY, can run some of the lower speed Ethernet protocols and be coupled with the MR-MAC. So 25 gig Ethernet, for example. And then similarly, the GTMs are the higher speed protocols, 56 gig, 112 gig PAM4, and they can be coupled to, say, the DC MAC or the interlock-in MAC in the right-hand side. So top right column, I think you already have an interlock-in MAC, a DC MAC, and at the bottom right, you have the GTY, and you can either couple that to a PCIe MAC or an MR MAC. On the bottom left, you have that SoC components, as I'd mentioned earlier, in the Versal Premium Adaptive SoC, which is the processing subsystem. So from Zinc, we went from a quad-core A53 to a dual-core A72 in Versal, and I think a dual-core R5 to a dual-core R5 in Versal as well. And then there's the CPM module, which is the coherency PCIe module. And in Versal Premium back then, at the time of launch, the C6 standard was prevalent. So the coherency piece of it was C6, and then the PCIe module offered Gen 5 capability, and hence CPM 5. Now we move on to what are the attributes of a domain-specific adaptive SoC. So the first thing is the subsystems involved are much larger. So what we've done is pre-stitch together the PHYs, the MACs, the accelerators into domain-specific subsystems. And because of that, your interactions from the programmable logic perspective, where in the adaptive SoC, the programmable logic had to either be a protocol-specific interface because it was interacting with the DC MAC or MR MAC, or in the case of the crypto engine, you were using a protocol-specific AES GCM interface. Here, it's very different because now you are dealing with these subsystems as a combination of different IP. And so you're dealing with them at a higher level of abstraction. So what you have is, due to the merging of multiple discrete IP in the adaptive SoC, in the case of domain-specific adaptive SoC, you now have a richer set of opcodes, because what has been architected into the system has to be made available to the programmable logic to make the calls and have the collection of IP perform certain functions. And so we've pre-configured certain connections, certain routes, certain pipeline acceleration stages. And so you, as a result, have a richer set of opcodes to interact with those domain-specific subsystems. And as I mentioned earlier, the focus is on performance and performance per watt. So you're no longer having to constantly hop back and forth between a programmable logic domain and a hardened IP domain. And so you get the benefits of data movement with higher efficiency, higher performance because of the ASIC logic running at significantly higher speeds. And so you're trading off that flexibility for significantly higher performance. And so as a result, now your interfaces are, user logic interfaces are to domains, right? You have to have your programmable logic adapter interfaces interacting with the specific domain. And, you may not need to use the entire opcode superset because there's a whole bunch of accelerators. You can choose, and depending on your use case, the specific subset of the opcodes from your programmable logic processing perspective and its interactions with the hard IP. And, the trade-off there is, again, a specific set of overlays, right? So the parabolic curve in the blue was narrower, the area under the curve was smaller in terms of the application space, but you had a significant rise in the performance and performance per watt on the y-axis. So that's how this comes about. So a really good example of the Zinc foundational technologies being deployed towards an adaptive SoC is the Zinc RF SoC with digital front-end enhancements. So this was our 4th generation RF SoC. And as you can see, there is an entire RF and digital front-end subsystem. And so that has all the hard IP required for very high frequencies, very high bandwidths, with very high rate of processing due to massive MIMO deployments. And so you've got the RF A to Ds, D to As, you've got some signal processing, you've got some filtering features. And so as you can see, even in this visual, the programmable logic is smaller. And so here too, they made a trade-off for significantly higher performance and significantly higher performance per watt. So you've got, the RF domain experts working with the FPGA experts to create an RF SoC that then creates a best-in-class performance and performance per watt product that would not have been possible if we had distributed those as discrete elements as part of an FPGA. So just to walk through the details, right? As I was mentioning earlier, whether it's a Zinc UltraScale Plus or Versal, you have a multi-protocol PHY that's interfacing with the outside world. You may have a PHY-specific programmable logic interface. And then this is not necessarily drawn to scale because in the PL, you may be doing some FEC logic or some link training aspects for that specific protocol, and you may be doing some additional processing. Then you hand it over to the Mac. The Mac, now you may have to do a protocol conversion to the Mac specific interface, and then you hand it over to the next stage of your pipeline, right? So you construct your pipeline. The other thing that I didn't dwell on before, but it's worth pointing out, is all those hard IPs tended to have cut-through memory, right? So if you really wanted to store information, you had to deploy FPGA resources, or maybe if your performance and capacity needs are such that you wanted to go to DDR, you would go off to DDR memory and store that somewhere there. But really, in terms of the interaction with the Mac, for the most part, it's cut through, right? The Mac itself is not sitting there storing a bunch of things for you to reference later. So you have to utilize VRAM, URAM, LUTRAM for the data movement or metadata movement between these different hard IP components. Similar situation with the accelerator, right? So if you were to use, say, the high-speed crypto engine, then on the left-hand side, you have to move, you have to create the protocol-specific interface for the HSC block. And the HSC block will tell you to put the keys and the security association in particular locations. So in programmable logic, you create the binding for that. And then again, on data movement, right? You're either giving the crypto engine security associations for the in HSC stored keys, or you're feeding those keys live because you've got millions of keys that you want to process over millions of flows. And so you're constructing the pipeline, you're figuring out how much PL memory will I use, whether it's URAM, DRAM, LUTRAM. And so you construct the pipeline, you create the resources, you create the protocol specific components. And that's how you have all the full flexibility, but you're using a lot more PL resources to achieve that flexibility, right? And then as a backdrop, in the case of Versal, of course, the data movement and the memory movement can be enhanced by the programmable network on chip so that you can even go from these different components from one component to another if you want it through the NOC, if you're not going through a hard IP component. And then, as I was mentioning earlier, you construct the pipeline. So you can figure out what order you want it, how often you may want to go back to a particular hardened accelerator. I'll take an example. Say on the left-hand side, you have a data center interconnect. So on the left-hand side, you've got multiple 10 gig connections over multiple MR Max or 25 gig connections, many, many connections. And then you process it through the MR Mac, then you move it to the PL. And then your intention is to take it out through a 400 gig port, multiple 400 gig ports to coherent optical networks for data center to data center interconnect. So you construct this pipeline. We offer adaptive SoCs that have that much IO, that many accelerators, that many Macs, and you take that SoC and you construct this very elaborate pipeline for your specific needs. You harness the AES GCM engine because you want to send the data center to data center information encrypted with the keys. Or the exact same adaptive SoC could have been used by somebody else for security firewalls, where all the inputs are the many, many 10 gig connections, and you're doing deep packet inspection in the programmable logic. And on the output also are many, many 10 gigabit Ethernet connections. So you can see how the same adaptive SoC physical device can be deployed across a wide range of use cases where you construct your pipeline, right? And so you're now dealing with a domain-specific adaptive SoC at a much higher level of abstraction, right? So the domain-specific interfaces are a conglomeration of multiple IP. And then as I get into the adaptive SoC for the SmartNIC DPU domain, you'll see the specific nature of the interactions that we have architected into the system. And similarly, the data movement now, because you are moving from multiple IP, you no longer have to deal with that cut through, and you don't have to dedicate PL resources in terms of LUT RAMs, DRAMs, URAMs, because the accelerator themselves will have either the data buffers or the metadata buffers for that data movement, for that pipeline acceleration. It's already built into the domain subsystem. And then, as I mentioned earlier, each subsystem, the granular view is it's a collection of PHYs, Macs, and we've built in those capabilities into the subsystem. So we had to kind of architect to either customer requirements or what we felt were the use cases we were targeting with this adaptive SoC. And so we provide the connectivity and we pre-configure it before you as a user get to use it, right? So now let's take that into the 400 gig adaptive SmartNIC / DPU SoC architecture. So on the top left, you have the host subsystem. The host subsystem contains the PHY, Mac, accelerators, data movers for host data movement. So those were architected by host domain experts. On the top right, you have the networking subsystem. The networking subsystem has its counterpart on PHY, Mac, and in this case, it's just the Ethernet protocol, and then packet processing. And again, those were primarily architected by the networking subsystem domain experts. On the bottom right is the memory subsystem. The memory subsystem has accelerators in there, and I'll get into those. And of course, the PHY and the DDR controller are already integrated into one. And the connections, again, are pre-configured into how you access those. And on the bottom left is the processing subsystem. And then interconnecting them all in the middle is the programmable logic. And you can see the programmable logic can directly couple to each one of those subsystems. And if you wanted to not use programmable logic resources for data movement, the programmable network on chip. So this is getting into a mix of, we've created new adaptive, domain-specific adaptive subsystems. And at the same time, we're leveraging all the foundational technologies from Versal and Zynq UltraScale Plus, right? So the network on chip is here as well. And then I'll get into some other attributes that we've forward propagated into this adaptive SoC. So zooming in on some details on the CPM5N. So earlier I had mentioned the Versal had a CPM5, Coherency PCIe Module 5. This is the next generation of it. The coherency has changed from C6 to CXL. So on the left-hand side, you see the combination of a tightly coupled PHY with the MACs, in this case, PCIe controllers. And then because of the CXL protocol reuses the PCIe PHY, and the training protocol that, when you link up, you train to a CXL protocol instead of a PCIe protocol. So what you have on the left-hand side is either a quad controller situation with PCIe. You can use a single controller for a Gen 5x16 connection, 2 Gen 5x8 connections over PCIe in the host subsystem. And like I said, the PHY is integrated in with this. It's tightly coupled. So as you go through these modes, we're pre-configuring the connections that you need to do. And instead of in the adaptive SoC, you would have to kind of connect those all in the pre-programmable logic. And then 2 of the controllers also can operate as CXL. And so in this case, you can have a single CXL Gen 5x16 bandwidth, 0.5 terabit per second bandwidth, or you can have a dual Gen 5x8 dual connection CXL to either a bifurcated single host or to dual hosts, depending on your use case. In the middle is a composable data mover. So it continues to have the traditional DMA capabilities for host to card, card to host data movement, but we've also enhanced it to be a data mover for on-chip data movement between the different subsystems. So as you can see from the arrow on the top, you can have data movement between, say, host data that has been read in through a DMA read, but then it's sent over to the networking subsystem because that's where the final destination is going to be out the network port, or the host data movement wants to go down to the processing subsystem, or it needs to go to the DDR. So you use the vertical connection, or you want to take the data and the host to card data movement. You want to take it into the processing subsystem, into the programmable logic subsystem, and so on the right. So the data mover is essentially a composable data mover. You decide how you want to move data. And so it's a step above a traditional DMA engine, which only does host to card, card to host data movement. You can actually do subsystem to subsystem data movement should you choose to, using the specific descriptor formats. And then on the right is the host data transform engine. And the host data transform engine does 2 things. For one, it provides host data transforms, and an illustration of that is AES XTS. So if you have file IO that you want to encrypt with the data at rest storage protocol, you can do so. And then there are other data integrity accelerators built into the host DTE. Now, I will focus on the horizontal lines. So in the case of the adaptive SoC, remember you had a direct interface into the MAC. Well, even in this host subsystem, it's host domain specific, we offer the ability to directly couple to the PCIe subsystem. So if you want, at a granular level, at the PCIe TLP level, you can continue to have programmable logic send PCIe TLPs over the PCIe controller specific interface protocol. In the case of CXL, you can have the type 1, type 2, and type 3 CXL flits transferred over to the programmable logic. And you can do the next stage of CXL pipeline processing for coherent device accelerators, right? So you can see the gray arrows from the horizontal axis going between the programmable logic. We kind of, if you think about it, this is a hybrid of the adaptive SoC technology and this domain-specific adaptive SoC. And we've obviously offered a lot more domain-specific features in the controllers. For example, the PCIe is not just a PCIe controller. It offers the enhancements with the PCIe IDE standard, which is the integrity and data encryption, which is AES GCM encrypted PCIe traffic. The PCIe TLPs themselves natively understand the protocol handshake with the host. And in addition to that, there is a new standard. The spec went to 1.0 last July. The PCIe TDISP standard, which is and this is my favorite, it's an acronym of acronyms. So it's T stands for Trusted Execution Environment, and then DISP is Device Integrity Security Protocol, or Device Interface, Trusted Device Interface Security Protocol. So TDISP. And so that offers a confidential compute zero trust, where you don't trust the host hypervisor, and even the endpoint device has the tenants have a host to tenant connection that is over what they call TDIs, Trusted Device Interface. So that capability is built into this. Now, from the programmable logic perspective, should you want, you can treat this entire subsystem as a black box. And you can use that rich set of opcodes on the rightmost interface. So you can see those 4 horizontal lines that directly couple to the host DTE. So those are multiple interfaces where you can do data movement and command movement and metadata movement at the macro level. So you use the rich set of opcodes and you just say, please go fetch this amount of data and move it through the processing steps in your accelerator pipeline, and then take it to a network domain destination. So now you've presented it with the black box opcode. And so now there's logic inside the host domain subsystem that will interpret that opcode and then do all the sequencing. So for example, you may have asked to move 8 kilobytes of data, and then the DMA engine will break it up because the PCIe max packet size happens to be 256 bytes, and then it'll take care of the host to card data movement, the reassembly, and then it'll move it through the accelerator pipeline. So it's taking care of all of those for you. And again, the trade-off is the opcodes are the set of pre-configured pipelines and pre-configured connection points and pre-configured modes that we offer you as a black box. So you can have both modes of operation. You can interact with the host domain subsystem at a granular level, just as you did with the adaptive SoC, or you can move to a higher level of abstraction. And your starting point is, hey, I don't need to spend all this time stitching together the Mac with the PHY and then go find that accelerator to bind to. That's all taken care of for me. And I orchestrate the movement at a higher level. Based on my policies that I want to do the data movement for different VMs through different network ports or with different encryption protocols for different services, right? So similarly on the network subsystem, similar theme, right? On the right side, you have a Mac integrated with the PHY. The interfaces offer 4x100 gig Ethernet connections or 2x200 gig. So unlike the adaptive SoC, where I was describing a very, very wide variety of connections to the outside world, here there is a fixed set of connections. You can deploy one of these two. Certainly the interface standards, even for 100 gig and 200 gig Ethernet, you can deploy it with 56 gig SerDes and use multiple transceiver lanes, or you can deploy it with 112 gig PAM4 protocol. So that capability is, so there are even within the particular Mac, and PHY interface, there is some configurability you can choose. In the center is the NIC, which has hardened all the standard functionality, whether it's your packet transmit buffers, packet receive buffers, 802.1 QBB. So all the policies thereof and the buffering thereof. The central block will take care of a lot of the standard Ethernet protocol and standard Ethernet RFCs. And then to the leftmost is the network data transform engine. And an example of the network data transform engine in this case is the AES GCM, where you can use it as standard IPsec protocol, or you can use it as bulk crypto because you have encapsulated packets with different keys, encrypting the different packet, encapsulations with different tenant keys versus maybe your cloud keys and such. And then there's also other acceleration built in, like checksum and other things where you don't have to perform those standard accelerator functions in your programmable logic. I want to just do a quick check on time. The way, yeah, okay. So I'll, memory subsystem, really, I just wanted to highlight that the crypto engines are built into the memory subsystem. So confidential compute is taking on significant relevance, both for data privacy reasons as well as security reasons in terms of, multiple tenants. Like I said, the processing subsystem has been significantly enhanced versus Versal. You have 16 core A78AE. We chose the A78AE protocol cores for two big reasons. One is the high level of reliability. These are automotive enhanced. And really in the hyperscaler world and in the cloud enterprise world, what will drive you nuts as a software developer is silent bit flips, and you don't know what's going on and whether it was a software Q&A issue that caused the system to crash or it was a bit flip. With the automotive enhanced, It's significantly enhanced the number of precise exceptions versus imprecise exceptions. So you know exactly what you're doing, what went wrong, where it went wrong, which thread. And so you can decide to either restart the thread, or you can decide, no, that was a critical piece of information and I need to reboot. So the low power domain has real-time cores. And so real-time cores are used for firmware development, for runtime operations, reconfiguration, and security protocols. For example, the IDE requires a key exchange mechanism with the host. So we've got a bunch of real-time cores with bounded latencies performing all those functions. And then we have a public key infrastructure. So, you know, it's very computationally intensive to do key exchange over the TLS 1.3 set of protocols. And so we have TLS offload for very high connection rate key exchange. Because with millions of flows, you're constantly having to replenish your keys, or new tenants and new VMs with new keys to be established for new connections. I'm going to skip through some of these slides and so sorry. So security is one thing that has propagated forward and then been significantly enhanced. You know, AMD Xilinx has a very rich history in working with tier 1 networking companies, as well as aerospace and defense companies and DoD. So we bought a lot of the security technologies from Zynq UltraScale Plus as well as Versal, and then we significantly enhanced it to create a zero trust capable device. So you now have, especially like, for example, government cloud, you have customers that don't want to trust the cloud owner, they don't want to trust the silicon provider. And so we provide cryptographic methods to ensure the zero trust, and then there's attestation so that you can at runtime ensure that your configuration hasn't been tampered with, and you know, a security vulnerability hasn't been created you know, within the system. So we have, and then through all the encryption standards on the PCIe IDE on the PCIe side, AES GCM on the networking side, and DDR crypto, you essentially have all data movement, data in flight, data at rest, data in use are all cryptographically protected from multi-tenant or tenant owner, any kind of policy you want to create. We have the flexibility to deploy every one of those models. So in summary, if you see from left to right, the system 1, system 2, system 3 are existing cards. Some of them have large FPGAs where it's doing all the work. In some cases, the card has multiple discrete components. We've added a processing SoC in addition to the FPGA. And then on the right is the topic of today's SoC conversation, where it's all integrated, right? So it's a large processing subsystem, a significant amount of networking, data path acceleration IP, as well as programmable logic. And then the orange lines are just to highlight the fact that they can all continue to be interconnected with the network on chip. So that's where we're headed, right? Going forward for that superior performance and superior performance per watt. So I mentioned there were 2 specific overlays you can do, right? This is one illustration. This is as a PCIe endpoint where the network and the host are being connected through SmartNIC/DPU functionality in the programmable logic. And then the exact same SoC can be turned on its head, and it's a headless server appliance. And in this particular case, I'm showing you a domain-specific overlay for NVMe acceleration. But you can see the hard IP, there are other applications that can be accelerated and deployed as a headless appliance in your data center. So people are doing domain-specific optimizations in the cloud today. They're creating custom devices that are optimized for a specific application, either for TCO reasons, performance reasons, or differentiation. And this particular adaptive SoC, the domain-specific overlays still give you quite a bit of flexibility, even though we've pre-configured and pre-routed a significant amount of hard IP. So really, you know, I want to finish with I wanted to do 2 things, right? I wanted to give you an insight into our thought process in creating the domain-specific adaptive SoC for the SmartNIC/DPU domain. What were the considerations? What are the trade-offs? And at the same time, I went through some fundamentals of the differences between adaptive SoCs and domain-specific adaptive SoCs so that you can imagine where we're headed, right? There will be other domains that could benefit from that significant uptick on the y-axis. And we will bring in those domain experts to craft subsystems to couple with other subsystems from the foundational technologies to create future adaptive SoCs. So with that, I don't know if I have time for questions, but.
I have a couple of short questions. Hello, very nice talk, thank you. So the parts question, the first one is this available now for purchase? And the second part is AMD also offer Pensando. Could you comment on the trade-offs? Thank you.
Sure. So I am from the hardware R&D group. There will be a product team that is figuring out how they will go to market. So there will be announcements forthcoming. As far as Pensando is concerned, so as I was describing the domain-specific overlays, one of the overlays you can put in FPGA fabric is the P4 domain-specific language. So in our case, the adaptive SoC from AMD Xilinx, P4 is one of the options, but it's not the only option. So different customers have different preferences. There are some customers that are bought into the P4 story. They like to do their pipeline processing and set up their rules in P4. Pensando has gone down that path. So their focus is on giving customers the capability to use their devices through the P4 programming interface. And so their tool chain is centered around P4. In the case of AMD Xilinx, we already have existing SoCs, right? We have the SN1000 SmartNIC card and such. So we want to be careful, right? We don't want to suddenly pivot. At the same time, it's not like we shut out P4. The P4, somebody can put together a P4 and we can offer P4 libraries to deploy the same. So ultimately, it's a little bit of a trade-off. If you're doing a lot of pipeline processing in P4, then you have to, and you're already vested in the P4 domain-specific language. Certainly, the Pensando offering is very attractive. And if you want either a certain level of customization in the programmable logic that wouldn't do as well in terms of performance, if you were to do those iterations in P4, the adaptive SoC has its sweet spot. So I think, if anything, I think AMD is now offering a very broad portfolio. And if you think about it, we're not walking away from adaptive SoCs, right? So there's a domain-specific adaptive SoC, and the Pensando DPU. And it's you pick and choose. And in some cases, a customer is picking and choosing both. They're deploying Pensando in one place and an FPGA-based solution in another place, because those characteristics are attractive to each of those locations.
Hi, this is James Hill from Carnegie Mellon. Very exciting technology. The question is also about programming. And I'd like to, whether you can say something about your longer term perspective on programming, in the sense that when we think about GPU, right? GPU started out an embedded graphics device, and now it's something that every user can program. It's truly programmable. Mm-hmm. And we look at DPUs, it's still very device-like. Then do you see with FPGAs down the road that DPU with FPGA becoming something like a GPU, if not a CPU, in terms of programmability?
Yeah, so this is almost my personal opinion. There has to be a compelling advantage, either the velocity of change, where you want to deal with a higher level of abstraction. I think in this particular domain, you're dealing with such a rapid increase in performance and performance needs and concurrency of different services that people are willing to invest in a closer to the device. There was a time when people programmed in assembly and then it moved to C, but now look at the proliferation of languages where the velocity of change, like Python, it's very attractive to program at a higher level of abstraction, right? I think it's a matter of evolution. I think the velocity of performance change and performance needs are so high. Certainly the software tool chain, you know, the AMD team is working very hard, and actually the Pensando and the Adaptive DPU team are working together to create the software infrastructure. But I think the velocity of change, the performance needs, things are just so dynamic that, you know, I translated to, for Formula One racing, you have a expert pit crew, you have a highly optimized vehicle, and you want uncompromising performance and performance per watt. So I think there will be, once things start getting where the velocity of change is more important than the raw performance, I think you will start seeing a standardization. And the P4 is actually, you know, Pensando is not the only company that has kind of gravitated towards that model of engagement. So I think it'll be a matter of time and need. It's just my personal opinion.
All right, great. I think it's about time to close this session. So let's thank Jaideep again.
Thank you.